welcome to the CP-31 Sheet Solutions. This is Vibhaas Srivastava, and today we'll be discussing problem 11 of the 1600 rated problems. So let's pull up the problems and let's open up the problem. Right, so problem 11, flexible string. You have a string A and a string B. Both of these strings have length n, and there are at most 10 different characters in the string A. You also have a set Q. Initially, the set Q is empty. You can apply the following operation on the string any number of times. Choose an index and a lowercase English character C. Add AI to the set Q and then replace AI with C. Okay, so we can do this operation any number of times. Choose a lowercase English character C, add AI to the set and replace AI with C. Let the string A be in the given example. So let the string A be ABCCA. And in the first operation, if we choose I equals 3, so that means this value, and C equals X, then we can replace E with X and the set Q becomes E. Right? And similarly, if we choose the sixth position after this, then this character will get updated. This character will become S, and the set Q will now be E comma A. Basically, the set Q is the set of all the characters which were changed at some given point. We can apply any number of operations, but in the end, the set Q can have at most k different characters. Okay, so under this constraint, we have to maximize the integer pairs L comma R such that the subarray from L to R in A and the subarray from L to R in B are the same. Okay, so let's have a look at it. Yeah, the constraints, let's have a look at the constraints since we should always see what the expected time complexity is. And we can see that n goes up to 10 power 5, right? N goes up to 10 power 5. Also, the number of unique characters goes up to 10. The number of unique characters goes up to 10 in the string A. In string A, okay? Now, usually when we have a constraint which is this unusual, this is a hint of some sort that this might be important. Okay, that we have like 10 unique characters in the string A. So we should always keep this in mind. And also n going up to 10 power 5 gives us hints that the solution will be n log n root n, or maybe n times k squared, something like that, right? These are the possible types of solutions which would pass. Okay. So now let's have a look at what the problem is asking us. So it says that there are at most 10 different characters in the string A, and we can replace characters, but our set Q must contain at most k different characters, right? So Q is the set of characters which we have chosen to be replaced, right? So let's break down this problem. Break down the problem. Break down the problem. So Q is the set of characters which we can choose to replace. So set of characters which we can choose to replace, which we can choose to replace, right? So the size of this set must be less than or equal to k, right? So the size of the set Q must be less than or equal to k. Basically, what that means is this is just some basic comprehension, is that at most k characters, at most k, or at most the characters, at most k unique characters, at most k unique characters can be edited, right? Basically, the operation is some kind of edit. We are taking a character and we are changing the character, and whatever the original was, we are putting it in the set Q. So basically, these k unique characters can be edited in the original string A, can be edited in the original string A. Okay, so that's what we know. That's what the question is saying. So at most k unique characters can be edited in the original string A. A has at most 10 unique characters. And we need to find out, what do we need to find out? We need to find out the maximum equal subarrays which we can have between A and B, right? So the maximum, find the maximum equal subarrays, maximum equal subarrays in A and B after this edit. After this, editing. Okay. So how do we approach this problem? Well, there are many ways to think about it. First, we can try and look for some greedy strategy, right? Some greedy strategy to find these k unique characters, and we can think through many different approaches. So obviously, there can be many possible different approaches. So how do we narrow it down to which approach we should use here? Okay, so we need to focus on the structure of the problem. So the first thing we observe is, so n, we know that A has at most 10 unique characters, right? So we know that, so we know that string A has at most 10 unique characters. Okay. So what if we have k greater than equal to 10? What if k is greater than 10, right? In that case, let us take some example A. Let us take the example A, B, B, C, C, D, A, B, B, A. Okay. Let's take some example B as well. So it has to be the same length. So we'll have, let's say, D, S, Z, A, B, B, C, D, B, A. Okay. So let's say this is our B. Now we want to maximize how many subarrays are common between the two strings, right? And the easiest way to do this is to assume that we make both the strings equal. If we make both the strings equal, we will definitely be able to maximize the common subarrays, right? The substrings. As you see, here A and D are different between the strings. B and S are different, right? And let's say C and B are different. D and B are different. And since we can change up to k unique characters, right? Here there are 4 unique characters in A. Observe that there are 4 unique characters in A, 4 unique characters in A, which are A, B, C, D, right? These are the only characters which are used to form the string A. In that, we can edit any 4 of them, right? So if we choose to edit A, that means that we can edit all the occurrences of A, right? And if we choose to edit B as well, that means we can edit all the occurrences of B, right? And we can edit up to 10. So that means we can edit all of them, right? We can edit all the 4 unique characters, and we can form the exact string. We can form the exact string B, and then we will have the maximum value, right? Then we will have maximum matching subarrays, right? Matching subarrays. Okay. So this is one example, right? So from this, what can we conclude? We can conclude that how many unique characters to replace? Well, we can conclude that. Let's just write observation 1. If let's say k is greater than number of unique characters in A, let's call that UC for unique characters. If k is greater than or equal to number of unique characters, then we can transform the string A into B. Then simply convert string A to string B, string A to string B. Right, wherever it is different, we can edit that portion, and then we will have our maximum count. Right, then we will have maximum count. This will give us the maximum count, obviously, all which are all the possible subarrays of the string, or all the possible substrings of the string. Right. So basically, this means how many can we edit? Basically, this means that the minimum of k and the number of unique characters, right? The minimum of k comma the unique characters. This is what matters. So if there is k is more than unique characters, then we have simply this solution. If k is less than unique characters, then we have to see what happens, right? So we need to find the case of, we need to uh, think about the case of unique characters less than k. All right. So how do we do this? Okay. So one thing we observed is if we simply convert the string A to the string B, it's going to maximize our count, right? So what if we can't do that? What if k is equal to 2? Let's say k is equal to 2, and let's take another example. So example 2, and let's say our string A is equal to um, A, B, C, D, D, C, B, A, A. Okay. And our string B is equal to A, C, D, E, F, B, X, Y, Z. Okay. This is our string B. And our k is equal to 2. That means that we can choose to edit any two characters. Okay, so if we choose to edit A, that means that we can only edit these A's. And let's say we chose to edit A and D, right? Our set Q is equal to A and D. So in that case, we can edit this, this, and this, right? And what should we do after editing? Well, it should be obvious that we should just convert it to whatever their values in E, whatever their values in B, right? Because if to edit, we choose to edit the values A and D, right? So everywhere where A is there, we should convert it to whatever value was then B. So for example, here A will remain A. Here D should become E, D should become F, A should become Y, A should become Z, right? So if we choose to edit the values of A and D, then at each position, simply make them equal to whatever the values at B, right? Simply make it equal to B of I, right? So, or basically what I'm trying to say is, um, if Q is decided, right? If the characters which we're editing is decided, if Q is decided, then for each A of I, if A of I is not equal to B of I and A of I is in Q, right? So if you want to write it formally, and A of I is in Q, then set A of I equals to B of I, right? And this is a greedy strategy. This is a greedy strategy that whenever we are able to change a given character, we should change it to the value equal to in B, right? And this should be obvious. So basically, the idea here is whenever we can edit a character, whenever we can edit a character, make it equal, make it equal to its target value in B, because obviously that will maximize the number of matching subarrays, right? Value in B. At least it will increase the number of subarrays by one, if not more, right? If we don't make it equal to that, it will not increase the subarray values at all. Correct? So this is our idea. Now, how do we figure out what our set Q will be, right? Now, how do we figure out? Now, how do we figure out? Do we figure out which values, which values of unique characters in A to pick, right? And usually, when we see problems like this where we have to pick some particular values, usually there's some elaborate greedy solution, right? But here there isn't a greedy solution, and the way you can figure that out is basically, if you try greedy for a bit, you will see that there's no clear-cut way to choose which characters are better than other characters, right? But the hint which we had was that there are at most 10 different characters, right? And it's written in bold also in the question that there are at most 10 different characters, right? So that should give us a major hint for how to solve this problem. And basically, since there are at most 10 unique characters, in how many ways can we pick the unique characters for Q? Well, there will only be 2 to the power um 2 to the power k, or 2 to the power number of unique characters, right? 2 to the power number of unique characters. You can just write it like this: choices, right? Uh, or since k goes up to 10 at most, so we can write 2 to the power 10 choices at most for what characters, for what unique characters we pick. So there will be at most 10 power 10 unique choices for what unique characters we're picking, right? So let's take an example. So basically, if you take the above string itself, you take the above string itself here, we can, let's say k is equal to 2, right? So we can choose either a comma d, a comma b, a comma c, or we can choose to replace b comma c, b comma d, right? So there are total 6 choices over here, as you can see. or C comma D, right? So there are total 6 choices. Um, and basically we can represent these choices using a bit mask, right? One way to represent these choices is a bit mask. So if we choose A and B, we can write 1100, right? If we choose A and C, we can write 1010. If we choose A and D, we can write 1001. Similarly for B and C, we can write it as 0101. B and D, sorry, B and C we can write as 0110. B and D we can write as 0101, and C and D can be 0011. C and D can be 0011, right? So basically, how many choices do we have? We need to choose. We need to choose from the total number of unique characters. Unique characters. UC, choose minimum of UCK, right? Basically this, and this will obviously be less than or equal to 2 to the power unique characters, right? So basically, we can see that the number of choices is not that much. At most, it's 2 times power 10, which is 1024, which is at most 1024. So one idea we have is we can try and brute force all sets, all of unique characters unique characters to choose, to choose, and see which gives us the minimum answer. Okay, and see which gives us the minimum answer, or sorry, the maximum answer, right? We want to have the maximum answer over here. Okay, so we can try and brute force all subsets, and this will take the go of 2 to the power 10 multiplied by f of how much ever um, time it takes, right? Time taken to check for a given, time taken to check for a given set, right? Time taken to check for a given set. And if we can do this in big O of n, if we can do this in big O of n, then 2 to the power 10 times n would pass, right? This would pass. So ideally, we have to somehow find out for a given set of unique characters, after replacing them, how many subarrays are matching. We should find that in big O of n somehow. So let's try and think of that. Okay. So basically, we have this sub problem, which we need to do in our brute force. Sub problem, given that we can replace, we can replace some characters. How many subarrays match with B, right? How many subarrays are matching with B, right? So basically, given two strings, how many subarrays are matching? That is what, or substrings are matching. That is our question, right? How many substrings are equal? So let's say we have like A, B, C, and then D, A, B, C, 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 A. Okay. And we have A, B, C, X, Y, B, C, A, C. Okay. So now observe here, this A will match, right? And also this B will match, right? The B will match, and so on. But if we manually count it, it will become n squared to match all pairs, right? But we can make the observation, and this is maybe observation 4, I guess, that if some subarray is matching, let's say from A, starting at A, up to C it matches, right? Beyond C it will not match. If some subarray is matching, then every substring or sub array will match, right? So basically, since ABC is matching, that means AB will also match. That means that BC will also match, right? So that's what we can say. And we can also say that, let's say here this does not match, so it's breaking the pattern. Then after that, if we go ahead, here again BC is matching, right? Here again BC is matching. Again, these two don't match, so nothing happens there, right? So basically, these are the like subarrays which match, largest possible subarrays which match, and every sub subarray, every sub subarray subarray within them will also match. Within them will also match, right? So how do we count that? Well, we can have any starting point L as here, right? So three choices for L, and for ending point we have two choices, any place ahead of it, right? So we can say that total number of ways to choose L now from basic combinatorics, or you would already know it for number of subarrays formula, number of subarrays formula, which is simply let's say the length of this subarray is L, right? So it will simply be L times L plus 1 by 2, right? Because we can choose L in um, L plus 1 different ways, right? We can have L here, 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 and then we can add them up. Basically, if we start here, then we have three ending places. If we start here, we have two ending places. If we start here, we have one position to end. So basically, it's like 3 plus 2 plus 1, right? So which is basically the n times n plus 1 by 2 formula, right? So that's the logic for how we can count the subarrays. So from this, we can observe that we can simply go from 1 to n, simply loop from position 1 to n, from position 1 to n, find these chunks of subarrays which match, find the of subarrays, chunks of matching substring between A and B, between A and B. Then we, for each chunk, we can add length times length plus 1 by 2, right? So we can add this to the total, right? And that will basically be the total number of subarrays which are matching. And we can find this in big O of n, right? We can find this simply in big O of n, right? We can find this in big O of n. So this brings us to our final solution, right? Our final solution, brute force all unique characters to replace, brute force all unique characters to replace, and we can do this using bit masks, right? Each character can be 1 or 0, whether it's being replaced or not, right? So using bit mask, so you need to know how to work with bit masks for this, like bit mask for brute force. Then this will be big of 10, 2 times 2 to the power 10, and then in that, for each count the matching subarrays, count the matching subarrays, and this takes big O of n, right? This takes big O of n. So the total time complexity will be big O of 2 to the power 10 times n, right? So to understand how to implement this, right? So even if you understood this, the implementation might not be easy. For that, let's have a quick look at the code for this, right? So I think the code will help explain it much better. Let's have a quick look at the code. Okay. So here's the code for the problem flexible string. Let's go through it line by line. So first we're simply taking in n and k and inputting a and b, right? And now here what we need to do is we need to know how many unique characters are there in our string, right? We need to know how many unique characters are there in our string. So this is going to store the unique characters. Okay, so this is going to store the unique characters in this array u, and basically it's also giving each character a position, right? So each character is mapped to its position. Why are we doing this? Because we need to use for our bit mask. For our bit mask, each character is mapped to position. If the character does not appear, it will simply be -1. Okay, if the character does not appear, it will be in -1. There are 26 characters, so it's pretty small vector, right? Okay, so as you can see, if this character is not appeared so far, its ID, or its position is set to the current size, right? And then we're pushing back this character, right? So we're storing the unique characters. We're also putting the ID as the current size. Now answer is going to be our answer, which will be the maximum across all the cases. Fine. U count is the size of the unique character, so it's simply the number of unique characters in A. B count is the bit count. Okay, so what is the bit count? It is the minimum of K and U count. And why are we taking minimum of K and U count? As we discussed earlier, what basically matters is minimum of K and U count, right? So if U count is higher, then k is the bottleneck, right? If there are more unique characters than k, then only k is the bottleneck. Otherwise, if k is higher and unique count is less, then this unique count is the bottleneck, right? So these are the number of characters we can change, right? So basically, over here we can just write it min of u count and k, min of k and u count is the number of characters we can change. Okay, number of characters we can add to queue, at most, right? What does this mean? This means change, right? The set queue is the numbers which we are changing, or the number of characters which we are changing, right? So that's it. And then we are going through all possible bit masks from 0 to 2 to the power u count minus 1, right? So we're going through bit masks from starting at 0 to 2 to the power unique characters minus 1. And why are we going in this range? We are going because if we replace no characters, then that's a bit mask 0, 0, 0, 0. And for example, if we replace the character A and C, then that's a bit mask which looks like this, right? And so on. So we're trying each possible replacement, right? And this is just a small optimization. Most probably the code will pass without it as well. But here is just checking if the built-in pop count, that means the number of set bits is not equal to this, then we can continue. Why? So this is a small optimization. It's not required, but it's helpful. Is that if number of changed characters, right? If number of changed characters, obviously if it is greater than if it is greater than minimum of k and unique count, then it's not possible, right? So it must be always kept less than equal to this, right? It must always be kept less than equal to this. But there is no point keeping it lesser. No point keeping it lesser, right? As you can see, there's no point keeping it lesser. So we are only checking. So we are only checking the cases exactly equal. Checking the cases exactly equal. Okay. There's no point keeping it lesser. We are only checking the cases which are exactly equal. All right. So now we are doing the matching algorithm. We need to keep track of what is the current subarray size and what is the total sum of subarrays, right? Total sum of subarrays which are matching. Now basically what we can do is if A of I is equal to B of I, or this value is turned on in our bit mask, right? So this ID, this character with this ID, that's why we created the ID array in the first place. If this character with this ID is turned on in the bit mask, right? That means that we are replacing this character. Or if A of I is equal to B of I, we can say that this is a match and we can just increment, right? We can say that this is a match and we can increment the size of the current subarray, right? So that's what basically we're doing here. We're like, okay, these two are matching, so we can go here. These two are matching, so we can go here. These two are matching, so we can go here. Then when we come here, they stop matching, and we can add 3 times 3 plus 1 by 2, right? So if they stop matching, else the count increases by match 1 by 2, right? Match times match plus 1 by 2. And now the number of matches becomes 0 again. Okay. In the very end also, we need to do this because what if it ends with an equality and then we do not add the match times match plus 1 by 2? That's why we're adding it here as well. Then finally, like we're brute forcing, right? So we need to take maximum over all cases. So here we take the maximum answer, ans equals max comma count, right? So this makes sure that ans stores our maximum value at the end. And yeah, that's about it for the code for this question. So we can analyze the time complexity will be in the worst case because we are brute forcing through 2 to the power 10 bit masks in the worst case. So time complexity in the worst case is big O of 2 times 2 to the power 10 times n time complexity. What about the memory complexity? We're not using any additional memory. We're just having the strings A and B. The memory complexity is simply big O of n, right? No memory complexity is simply big O of n. And that's about for this question. If you had some trouble solving this question, well, yeah, this question did use some concepts across a lot of diverse domains. So the topics used over here were mainly it was time complexity slash brute force, understanding how time complexity slash brute force works, right? Also bit masks was used, right? So some understanding of basic bit masks, not advanced like bitmask DP, very basic bit masks on how to brute force using bit masks, and then some basic combinatorics idea, like how to count the number of subarrays, right? So basic combinatorics. So if you had any problem with this question, you should definitely check out strengthen these topics, right? Thank you. Hope you learned something. If you didn't understand some portion, do rewatch it. Do go through the code. Go through the code with an example step by step. That does teach you a lot, right? Rather than simply watching the video. Okay, thank you and see you in the next solution.